Hey everybody, it's Ripley back again. Today we're going to talk about continuity. All right, now continuity, continuous. Let's see, the heuristic way of defining continuity is really simple. I'm going to take a little drink of my tea here, so give me a minute. Sorry, I need a little caffeine. The heuristic way of thinking about continuity is pretty simple. If I can draw a function from left to right without lifting my pencil, then that function is continuous. Okay, now that's a super oversimplification, but it's not unhelpful. Let's put it this way. So let's look at our function f of x here. We know that the limit as x approaches a of f of x in this case appears to be L, right? But there's a problem. At L, well, let's review really quickly. Why does the limit as x approaches a of f of x equal L? Well, as I sneak in from the left, I sneak in from the right, my fingers would touch if I didn't have dental floss draped over x equals a. Right, so I got that. That's easy. But to say that it's continuous is wrong, isn't it? Because if I want it to be continuous, I need this guy, this what appears to be a comma f of a, up here. It's in the wrong spot, isn't it? Because I've got to lift my pencil to draw that spot. So I need to stuff that thing down in there if I want this function to be continuous. So if you think about it, the limit as x, if I want a function to be continuous at a point, then the limit as x approaches a of f of x, not only do I have to have the limit exist, which it clearly does in this case, but it also has to equal f of a. This statement right here implies that f of x is continuous at f of a. Or excuse me, at f of a. Somebody slap me. At x equals a. All right, so that now what we have is called a point continuity. Now if a function is not continuous at a point, then we call that function, or we call that point, a point of discontinuity. So in this case, the one that I just drew, this would be discontinuous, continuous at x equals a, okay? Excuse me. All right, so we've got discontinuities and we have continuities, okay? And we have to understand how to determine using limits. You can look at a graph and be like, Rip, this thing is discontinuous at x equals a. I have to lift my pen. It's got this point up here when it should be in there. You're absolutely correct. But being able to prove it with limits is very important, okay? Now, let's talk about what it means for a function to be continuous, a continuous function. A function is continuous. Now, this is where I get lazy. CTS is an abbreviation, all right? Is continuous if and only if it is continuous for every value of x. All right? Now, this is where it gets a little bit confusing. So this would be like a polynomial. Do we agree that a polynomial is continuous everywhere? However, we can say that a function is continuous on its domain. A function, and some texts won't parse this out, and it kind of drives me crazy when they don't. A function is continuous on its domain if and only if it's continuous for every value of x. I could write this as x equals a if I wanted to. I guess I'm being a little silly. In its domain. Now, let me make sure that I distinguish the difference here. Okay? Look at f of x equals 1 over x. If f of x is 1 over x, we know what this looks like. Quick sketch, terribly drawn, is this guy. Clearly discontinuous. It is not continuous for all reals. So we say that it's not a continuous function, right? And the words can get really confusing here. However, f of x, I should just say 1 over x, equals 1 over x is continuous for every value in its domain. Is continuous for every value in its domain. Okay? You with me? So clearly not continuous because the limit doesn't exist at x equals 0. Let alone the function existing, there is absolutely no way to show that the limit as x approaches 0 of f of x equals f of 0, right? Because there's A, there's no limit, and B, there's no f of 0. They don't exist. Now, what about a function like f of x equals the square root of x? Here comes root x. Looks like this guy, right? This is y equals root x. Remember, y just equals f of x. Well, clearly, for every value not equal to 0, I know that the limit as x approaches a of the square root of x equals the square root of a. So we're good, right? I mean, this equals f of a. Nothing to it. Therefore, we're continuous. There's a problem, and that's at x equals 0. All right, so first things first, I am absolutely in trouble because when I try to take the limit as x approaches 0 of the square root of x, we are in frowny face mode. I can't approach from the left. I can approach from the right, but I can't approach from the left. Well, your spidey sense is probably tingling. You're probably saying, but Ripley, can't we take the limit as x approaches 0 from the positive side of the square root of x, right? I'm sorry, positive side of 0 of the square root of x, and this equals the square root of 0, yay, which is equal to f of 0. Exactly. That is exactly correct. And the way that we deal with that is we say this implies that f of x is continuous from the right. And we have to come up with this distinction from the, I don't know what that is, from the right. All right, because we approach from the right-hand side. And the reason that we have to come up with this distinction is because, like, f of x is a well-behaved function. We like it. It's delicious. It does good things for us, and we use it constantly. But we have this point of where formal continuity is lost, because I can't take a limit from both left and right side. We still want to play at 0 on the square root of x. So we say, okay, we're continuous from the right. We're hedging the bet because we have to. If I want to be able to play games with the square root of x, then I can only approach it from the right-hand side. Similarly, if we had some crazy function, let's see, I don't know, f of x equals, I'm going to keep it simple, negative root x, which we know hopefully looks like this. Well, hopefully you can tell that we would have to take the limit as x approached 0 from the negative side of f of x, which is the square root of negative x, right? And this is going to equal square root of 0, which is equal to f of 0, which implies f is continuous from the left. So what this enables us to do is play around at endpoints. Now, why is that important? Well, not only is it important for functions like the square root of x, which we just talked about, but it's important, let's say that I have some crazy function. Let's just some crazy polynomial, right? Let's keep it simple. This is f of x, some crazy polynomial. What if I'm only what if I'm only playing ball with f of x on the interval from a to b? Okay? Now, think of this interval from a to b as being kind of like looking at the function through binoculars. Well, the function was continuous. Clearly, all polynomials are continuous for all reals. We already talked about that. The function was continuous before we showed up, and all of a sudden we start looking at it, and now clearly still continuous for all values between a and b. But what happens at a and b? Well, if the function is continuous, then it's got to be continuous at those endpoints, right? It has to be. However, because we're only looking at it on a closed interval from a to b, I cannot take that limit, right? I'm not allowed to take the limit from both sides because the function, as far as we're concerned, f of x on a closed interval from a to b, as far as we're concerned, anything less than a doesn't exist. Anything greater than b doesn't exist. So we have our fancy little, we say that f is continuous from the right at x equals a, and f is continuous from the left at x equals b. And this is going to become really important when we start getting a little more deeply into the differential calculus. Okay? All right. So, excuse me. Bringing up the interval is kind of nice. We can say all of this leads to an interesting little definition. I know that f is continuous on the closed interval from a to b, all right, if it is continuous for every value on the open interval from a to b, and continuous from the right at x equals a, and continuous, sorry about my handwriting, I'm down here on this little pad, I'm drawing near my belly button, from the left at x equals b. So that's how we define continuity on a closed interval. Now, this is a whole lot of smoke and a little bit of fire to really make us realize that, okay, look, it's obvious we're going to be able to look at functions visually and determine whether or not they're continuous on closed intervals. Where the rubber meets the road with these definitions, this continuity from the left, continuity from the right, and continuity on a closed interval, is when we can look at a function. When we're dealing with functions that we're either not graphing, or we kind of don't know how to graph, or we don't know how they look at, or excuse me, we don't know what they look like. All right, so this is going to lay the foundation for the rest of this section. The rest of this section doesn't take very long, so just bear with me. But I want our definitions of continuity in general, from the left, from the right, on closed intervals, to be firmly in place. And you need to know when a function is continuous and how to show that it is continuous graphically, numerically, algebraically, all of those good things, just like we did back in limits. All right, so I'll meet you back here in just a second. I'm going to take a little break. Excuse me, and then we'll talk about some of the ramifications of our definitions of continuity, and then we'll be done. Okay, I like you guys, even though I don't know you guys. So I just sort of, this is like a cooking show. Poof, up pops a theorem. All right, let's go through this theorem really quickly. It should be relatively intuitive, especially since continuity comes from limits. Continuity builds on limits. So let's look at the theorem really quickly. Suppose f and g are continuous at x equals a, and c is an arbitrary constant. Then, 1, f plus or minus g has got to be continuous as well. That should be relatively intuitive. 2, a constant times f is going to be continuous as well. F times g is going to be continuous, and last but not least, f divided by g is going to be continuous, provided g of a is not equal to 0. G of a equals 0, you got issues. Unlike limits, where, oh, let's do a little algebraic two-step and cancel out that denominator, you're screwed. You lose continuity. Once you have 0 in the denominator, continuity goes out the window. Okay? All right, now let's talk about a bunch of functions that are continuous for all values in their domain. So they are continuous on their domain. All right, first and foremost, so functions, continuous on domain. Now remember, this is different than being continuous for all reals, or what you'll hear is just being overall continuous. All right, functions, continuous on their domain. Well, polynomials are continuous for all reals, right? We got polys. We got rationals. Now, you're saying rationals, wait a sec, Ripley, doesn't that produce vertical asymptotes in rational functions? Yes, but we're not talking about the values of the vertical asymptotes. We're talking about on their domain. So rationals, roots, we already talked about roots, root functions, trigs, all the trigs are. In other words, there's no popping around where we got to worry about this. Even though we have vertical asymptotes in trigs, tan, cotan, secant, cosecant, all the trig functions are continuous on their domain. Sine and cosine are continuous for all values. All right, inverse, the inverse trigs. Let's see, what am I missing? Oh, exponentials. And then if exponentials are continuous, then their inverses have to be logarithmics. Now, there are more functions that we could say that are continuous on their domain. We can build them out like combinations of all of these, but just know if I'm required that a function be continuous, and I'm dealing with these functions right here, this list of functions, then I'm allowed to say that they're continuous on their domain, and I'm allowed to play ball from that. Okay, I'm going to formally define something that I said back in limits. Okay, this is an actual theorem. All right, and the theorem says this: if f is continuous at A and the limit as x approaches b of g of x equals A, then this implies that the limit as x approaches b of f of g of x equals f of A. Now, you may be like, wait, what is who, huh? Well, what this really says is the limit as x approaches A of f, oh, should I say f as x approaches, well, let's leave it as x, what the heck, I'll have it approach b, sorry. I've got to stay consistent with my notation, I confuse myself. Limit as x approaches b of f of g of x is actually equal to f of the limit as x approaches b of g of x. In other words, I can stuff the limit into the composition, and that's really important. It's really useful. It's very helpful. However, let's look at this. F has to be continuous at A, right? And the limit as x approaches b of g of x has to equal A. So when I plug in b into g, I got to get A. So now I'm just talking about f of A, which we know it's continuous at A, so I'm allowed to do that. So look at what happens here. Let's parse this out just for a second without getting too nuts. When I plug b into g, I get A. And then I just get f of A when everything is said and done. Now you may be saying, Ripley, why are you bringing this up now? Well, again, look at what this says. This says the theorem. This is another theorem about continuity. Suppose that if g is continuous at A as opposed to x, I'll just write x equals A. Whoops, at x equals A. And I know I'm flipping around my A's and my B's, but don't be afraid. It's good. And f is, I want there to be a difference between what we do with the continuity and what we do with the limits. Okay, so suppose g is continuous at x equals A and f is continuous at g of A. Okay? This implies f of g. Now, hopefully you've seen this notation before. This just means g composed into f, right? F of g, which is also the same thing as f of g of x. This is typically how I write this. Sometimes you'll also see this. I hate this notation. Just because it takes, I don't know, it seems counterintuitive and you're worried about multiplication. It doesn't matter. Don't listen to me. Is continuous at x equals A. Now, this is, so the whole reason that I had to do this guy, this right here, this theorem, is remember, limits or continuity is defined by limits. So I have to be able to take that limit, in this case, at x equals A, right? And I know I defined it over here as x equals b, but we're not afraid of that. So really what it says, think about it this way. If I compose continuous functions at values of continuity, then the composition is continuous as well. So how could we turn that into like a little sing-song thing? The composition of continuous functions is continuous. That's an interesting way of saying it. Okay, one last thing, then I'm done, which is cool. This is called the intermediate value theorem. It is the first, the intermediate, of your value theorems. In differential calculus, you will have 3 of these. The intermediate value theorem. And this one's super straightforward. Theorem. You'll see this written as, I'll write it in my class, if you're taking class from me, as the IVT. Super simple. All it says, excuse me, is suppose that f is continuous on the closed interval from A to B. Now, I'm going to do something a little funky here, but don't panic. When I'm done, it'll make sense. All right, we're going to let n be any number between between f of A and f of B. All right. Now, what the IBT ensures. Oh, by the way, we're not saying that f of A and f of B can be equal. So I should probably put and f of A not equal to f of B. Okay. What the intermediate value theorem implies is that there exists, okay, this backwards capital E is just math speak for there exists or there is, because we're lazy and we like concise notation that makes us look really smart. There exists a C on, this is an element of A, B, this is the open interval. So somewhere between A and B, there exists a C in that open interval such that f of C equals n. Now, what this is just fancy speak for if I've got a function, all right, here's my function, and my function is guaranteed to be continuous. That if you don't have continuity, then you can't use the intermediate value theorem, period. And let's call this A, and let's call this B. Therefore, this is going to be f of A, and this is going to be f of B. What it really says, what the intermediate value really says, is that we are guaranteed to pick up all of the values between f of A and f of B. Pick any n in between and there's going to be a C. So let's say I pick this n. I cruise it over. Let's change colors. I cruise it over. I pick up my value right there. There's going to be a C such that f of C equals n. So I get this point, C comma f of C. Now, let's be a little bit careful here. Okay? If my function does this, like that. All right, so now we're calling this f of x. And let's call this A, and let's call this B. Now A, let's see, I'm going to cheat a little bit. This is f of A, and this is f of B. But your function's doing all this janky stuff here and here, right? Well, the intermediate value theorem only guarantees values between f of A and f of B. See how it says? Pick any number between. We got no guarantees above f of B or below f of A. Now, where was this used? Well, this isn't even a calculus theorem. This was used early on, back in the day when they first started dealing with function theory. Let's say you had a polynomial, right? And you had a polynomial that did something like this. They knew that polynomials were continuous before calculus, and they said, okay, let's assume that we've got a value down here at what's that look like? 1, 2, 3. This is going to be 4 comma negative 2. And then we got a value over here at 6 comma 1. All right? So what does that tell me? If I've got a continuous function, I'm going to call this p of x since it's a polynomial. If I've got a continuous function and it starts at negative 2 and it ends at positive 1, there has to be a 0 in between. That was the first practical usage of the intermediate value theorem. But we're going to use this quite a bit. It's a relatively important theorem, and it's one of the big 3 value theorems that we use in differential calculus. Okay, cool. That's enough. I'm tired of talking to you people. Have a great day, and I'll talk to you soon.